Now the okay.
I'm making the computer.
All right, so intermediate value theorem, let's kind of wrap this up and then you guys can work on that assignment. So, different kind of question here. Click them all closed, have a look. It says find the values of C, you know, whatever you want to call it. Some, I think in our textbook they call it C. The values of C guaranteed by the intermediate value theorem, where f of x equals 18, if A is just, if a value of C is guaranteed. In other words, first of all, we got to figure out, does it apply, right? And the kinds of questions you're going to get, it's going to say, does it apply? If not, why not? You'll list why not. If it does apply, then we have to just go find the place. But that's not even calculus stuff, right? That's just a little bit of algebra too. So here's the function. Here's the closed interval. Is there a value of C guaranteed? How would we know? What would we do to check? What are the criteria for the mean value theorem? It's always, you're filling in the blank. With any one of these existence theorems, they're always in the form if criteria, then something's true, right? So what are the criteria? Yes, sir?
It has to be continuous.
It has to be continuous, right?
Yeah.
It has to be continuous on the, you know, we had that debate yesterday, right? Is it an open interval or a closed interval? But it's continuous on the interval, right? That's check. And then what else in order for the intermediate value theorem to apply? That's the first criterion. The second one is what? What it has to do with this 18.
Yeah, it goes through that point.
Okay, so 18 is a value that's between
Yeah.
the value of the function at A and the value of the function at B, right? So those are the things we'd have to check. Well, let's check the continuity issue first. So is f of x discontinuous anywhere? Oh, yeah, absolutely. Is f of x continuous on our interval? Where's it discontinuous? At 2. Okay, so the only place the function is discontinuous is at 2. Is 2 on our interval?
No.
Okay. Actually, it is, isn't it?
No.
Oh, no, it's not. Never mind.
I was like-
Oh, we're good. Yep, sorry.
Unless two
Brain fart.
automatically
Brain fart. Must be Friday. Long week. Yeah, so we're going from 2.5. I was thinking we were 3 times. Yeah, so we're good. So it's discontinuous outside of our interval, so we're fine. Check box number 1. Box number 2, let's evaluate the function at 5/2 and at 4. And if we do that, we end up with, and we can just, you know, do this. We can do this on technology if we want to. So at 5/2, we get a value of 55/2. At 4, we get a value of 14. So is 18 between those values?
Yes.
It is, right? 18 is greater than 14 and less than 55/2. So we can check the second box. So it does apply, right? So now we have to just go find the value. Well, how do we do that? It guarantees at least one place where our function has a value of 18. What do we do? Set it equal to 18. Ask the math gods, right? Set the function equal to 18, and you know, and they'll tell you through algebra, right? So if we set our function x squared plus 3x over x minus 2 equal to 18, we just got to solve that equation. So how do we do that?
That looks like it's 30.
So what can I do?
Multiply by x minus 2.
Multiply, so cross multiply. Right, I have a proportion here, don't I? It's 18 over 1. Good, so we get x squared plus 3x equals, if I distribute, I get what, 18x minus 36, everybody agree?
Yes.
Okay, now what?
Set it equal to 0.
Good, put it in standard form,
Yeah.
set it equal to 0. So x squared, if I subtract 18x minus 15x plus 36 equals 0. Now we've got a quadratic equation in standard form. So real quick, what are our options? We deal with this a ton, all the time. How do we solve a quadratic equation in standard form? What's our easiest option if it works? Factoring. If factoring is easy to do, we do it. If it's not easy to do, then what?
Quadratic formula.
Quadratic formula or complete the square, whatever you prefer, right? Okay, so Are there magic numbers here that multiply to positive 36 and add a negative 15?
Yeah.
12 and 3. Okay, good. So we get x minus 12 times x minus 3 equals 0. So my solutions are x equals 12 or x equals 3, correct?
Yeah.
Not quite. Look at the original problem.
It has to be in between.
Okay, yeah. So the only value guaranteed by the mean value theorem is the value that's on the open interval between 5 halves and 4. Make sense? Okay. So this is the solution guaranteed by the mean value theorem. This one is extraneous in the sense that it's outside of the purview of this problem. Right? It's still a solution, but it's not the one that has nothing to do with the intermediate value theorem. Okay, make sense? Okay. All right. This is kind of a cool problem. This is a math problem. You're getting to a point now where you can actually do stuff. For the first time, you can do something real in math. It's just not all just practice. Everything's been practice leading up to calculus.
So I've done 11 years of practice for the flow network.
Yes.
That interesting.
And this is a pretty cool problem. Pretty cool that we can address this issue now, logically, mathematically. You probably have a sense this had to be the case.
Probably at the age of 30.
So 8 a.m. on Saturday, man begins running up to his weekend campsite on the mountain. On Sunday morning at 8 a.m., he runs back down the mountain. It takes him 20 minutes to run up and only 10 minutes to run down. At some point on the way down, he realizes that he passed the same place at exactly the same time. Well, does it have to be that way? I mean, think about this just ignore the math for a second. Do you get a sense that you have to pass by the same place at the same time at least once, or could every place that you pass be at a different time on Saturday versus Sunday? See what I'm saying? If you're starting at 8 o'clock both times, is it possible that you never pass by the same place at exactly the same time of day you did the previous day? Or is there at least one place where you have to pass at the same time? Interesting question. Common sense probably initially would say, oh, no, you don't have to pass by the same place at the same time, right? It might all be different. Okay? What do you think? Let's think about this in terms of intermediate value theorem. And we can prove that that's not the case. We can prove that, in fact, you have to pass by the same place at exactly the same time. It's mathematically essential. There's no way around it. You have to do it one time if you're not backtracking. It's going to happen once. Right? How come? Well, let's define a function. If we say that S of t is the position, your distance from the trailhead, let's say, on Saturday, and R of t is your position relative to the trailhead on Sunday, right? Well, how far up is it? We don't know. Say it's a mile, right? Say it's a mile. Well, if f of t is going to be your position on Saturday minus your position on Sunday, okay, is that going to be continuous? First of all, is your position function continuous? Let's just take Saturday, the position function for Saturday. If it's S of t is my position as a function of time, could that possibly be discontinuous? In order for it to be discontinuous, what would have to happen?
Time systems versus
I mean, yeah, you'd have to, in order for that to be discontinuous, you would somehow have to be able to travel from here, like over to here, in no time at all, right?
Just think
Because
about it.
each
Time
of the
machine.
infinite, I mean, your position is, let's just say, let's just ignore modern physics and say your position is infinitely subdividable, right? So there's an infinite number of places that you can step between the trailhead and the campsite, right? Infinite number of places. You can't skip over any of those. You have to go through all the intervening space, right? And time runs continuously from, when you start to when you stop. And so, of course, that has to be a continuous function. There's no way it could be discontinuous. It's not physically possible. Same thing coming down, right? And if I take a continuous function minus a continuous function, it's a continuous function, right? So this is definitely a continuous function. Your Saturday's position minus Sunday's position. Okay? Well, if that's a continuous function, right, and the starting value is going to be, starting value is going to be what? At time 0, Saturday's value, S of t is going to be 0, isn't it? Right? R of t is 1, assuming we're talking in miles, right? Okay, it takes 20 minutes to run up, 10 minutes to run down. So after 20 minutes, it's going to be 1 minus, is that right? 1 minus 0, correct? Get that right? Did I get that right? Yeah.
Yeah.
It's going to be 1 minus 0, right. So we're going from a value of -1 to +1 miles. On Saturday, did everybody see what I'm saying? Let me write that down. So f of 20 is going to equal s of 20 minus r of 20. So after 20 minutes on Saturday, we're at the trailhead. Agreed?
No,
Saturday's when we're going up.
we wouldn't be at
So
the
we're-
trailhead. We
Oh,
would
sorry,
be
I mean, we're at the
campsite.
campsite,
Okay, okay.
campsite. So our distance is going to be +1, right? Sunday, after 20 minutes, we're at the trailhead, which is 0 miles from the trailhead,
Yes,
okay? That make sense?
yes.
So f of 0 is going to be s of 0 minus r of 0. So on Saturday, at time 0, we're at the trailhead, right?
Yes.
On Sunday, we're 1 mile away from the trailhead. So we get an answer of +1 at f of 20, and f of 0 is going to be -1, right? Well, what would be the value of f when the guy passes by the same location at the same time? 0, right? Isn't it? Because that's when S and R are going to be equal. The distances from the trailhead on Saturday and Sunday would be the same, correct? So the value we're interested in is when is the position function f equal to 0, because that's when that magical event happens. Well, by the intermediate value theorem, it has to happen at least once, doesn't it? Right? Okay, so can you come up with, and this is not very mathy, but this is a lot of times what math is about. Can you come up with a really elegant way, just sidestepping all the math, of proving the same point without having to even invoke the intermediate value theorem? It's cool that we can, right? And it works. We just showed that it works. But could you come up with kind of just a thought experiment that would illustrate that much more simply and elegantly? Could you prove to somebody, just beyond a shadow of a doubt, that, yeah, you definitely go by the same place at the same time? I'll leave you thinking about that. Go back to it. Okay, so we'll come back to that one. I'll see if you can get it. It's really simple. So this isn't anything, kind of any highfalutin math or anything. This is just a simple way that you could demonstrate logically that it has to happen.
Do graphs help in showing it mathematically?
They do. This isn't even having to use a graph, but you could. A graph might be nice. That'd be a good way to illustrate the math.
Are we just using like people walking?
Sure.
Redmond, stand up.
Right now?
Right now.
What?
Yeah. You walk. How do we think this through?
This is your idea of the code.
Yeah. Just follow directions.
When you start walking, but Redmond starts walking faster, imagine you're the person going up, Redmond's going down.
There it
You
is.
guys would cross.
There it is. So instead of, right, you get the idea? So we say, instead of having it be on Saturday and Sunday, just say it's the guy's twin, who walks exactly at his speed, and they do everything identically. If some guy walks down on the same day as the guy's leaving, if the guy's walking down and it takes him 10 minutes to come down the mountain, whereas the guy walking up takes 20 minutes, they're going to pass by each other on the trail, aren't they?
I was getting way
Drop
too
the
into
pin,
it.
that's it, right?
I was getting
So we just proved it.
I think we do that.
All right. Couple challenging limits, let's look at these. And then I picked these. These are just kind of related to some of the challenge questions I gave you at the end of the assignments. They're not worth very many points. But there's some good math here I want to review with you. So evaluate these limits. Let's evaluate the limit of this function as sine, or as x approaches pi halves. So unsurprisingly, if I plug in pi halves, what do you think I'm going to get?
0 over 0.
Yeah, because what is sine of pi halves? So do you instantly think unit circle when I say stuff like that?
Yeah.
I'm trying.
Okay, good.
I just.
Good. And I want to do a day, we're going to do like a unit circle day where I just do nothing but unit circle. It's 1, you're right.
Yeah.
You're right. So we end up with 1 squared minus 2 times 1, or plus 2 times 1 minus 3 is 0. On the bottom we get 1 minus 1 is 0. Okay. So how in the world could we deal with this? And there's something really important that I'm kind of trying to drive at here, that I want you to get good at doing. Because I'll tell you, it's amazing. Trig is a reality. Like I would say that in my career as an electrical engineer, I use trig like more than, I mean, it's all here is calculus trig. And that's what you do. Trig is the world. Yep.
Yeah, that's what I was saying.
Okay, good. So this is the key. What you want to always kind of, when you're looking at things like this, you want to see the trig functions, like you want to see sine squared of x as the quantity sine x squared. You want to see the trig functions as being individual entities that you can work with algebraically, just like variables, right? So we could factor the top, right? This is the same thing as saying, or it's similar to saying x squared plus 2x minus 3. Well, you can factor that, right? Okay, so we can factor this. So on the top, what would that factor into? Sine x
Plus 3. Sine x minus 1.
divided by.
Sine x minus 1.
Everybody see that?
Yeah.
Okay, because remember, this is shorthand. Sine squared x is just sine x quantity squared, right? Okay, and the limit as x approaches pi halves, well now what can I do that's handy?
Cancel.
Yeah, I cancel the offending factors, the ones that are causing the indeterminacy, and now we're good. Now we can evaluate the limit directly. So what do we get if we let x go to pi halves? 4. Right? Okay. How about this one? Last one, how about you?
Oh.
So this one is not going to be indeterminate, is it? Right? If I plug in pi fourths on the top, would you agree there's no way I'm getting 0 on the top? Right? But on the bottom, what is tangent of pi fourths? 1, isn't it? Right? And once again, just think unit circle. That's horrible circle, sorry about that. Pi fourths is right there. Well, that's going to be the location where the x and y coordinates are the same, isn't it? Right?
Yeah.
Tangent is just, sine over cosine, so it's going to be the y coordinate divided by the x coordinate. So we're getting 1 there, aren't we? So this is, I'm getting 0 on the bottom, right? So this is a does not exist, but I'm giving you the direction from which I'm approaching pi fourths, and so I want more than that. I don't want just does not exist. I want to know which infinity is it, positive or negative. Okay? So how am I going to do that?
Well.
On the top, am I getting, I guess we could figure out, I'm getting what on the top? Positive or, it's got to be positive because that 7's big, right?
Yeah.
Pi fourths is something slightly less than 1, right? 3.14, blah, blah, blah,
Yeah.
divided by 4 is slightly less than 1. So 3 times something slightly less than 1 squared is slightly less than 3, right? Minus something slightly less than 1, doesn't matter. 7's going to outweigh it.
And the root?
So, yeah, that's weird. So on the top, everybody agree, we don't care what it is. We know that when we evaluate this directly, we're just getting some positive number.
Yeah.
Yeah.
Okay. But what about the bottom? That's the key. We're getting a 0, but is it a 0 minus or a 0 plus?
To 0.
Okay, what's our thinking? How do we approach that?
Well, if you're coming from the right, like,
So you're talking about maybe looking at a tangent function.
yeah.
That's fine. We can do that. We can look at a tangent function. So if we were to think about the graph of tangent, what is the graph of tangent?
Spent summer.
Isn't like
It
mu?
starts, it goes up.
Okay, yeah, so it's going to be asymptotic. It's going to go like
Just kidding.
that, right?
Yeah, that's right.
And then we're going to get these repeated asymptotes.
So positive.
Well, it's coming from the right, it's coming.
Okay, so it's coming from the right, isn't it?
Yeah, so it's gonna be negative
It's coming from the right, and where are the asymptotes?
on.
Pi over 2.
Tangent sine over cosine. Where's cosine 0?
Pi over 2.
Yeah, so they're going to be at pi halves. That one's going to be at pi, then 3 halves pi.
Can't hear everything you say.
So the value, the point we're looking at is at pi fourths, which is going to be right there,
Yeah.
right? What are the coordinates of that place? Well, the y value is 1, we say, right?
Yeah.
So if we're approaching from values greater than pi fourths, the ant is walking down the function towards that point from the right, correct?
Mhm.
Yeah.
So his values are going to be 1 plus or 1 minus.
From the right.
Plus, right?
Yeah.
Because he's walking from the right, so he's walking down like so. He's walking from values like 2, 1.5, 1.1, 1.01, 1.0. See what I'm saying?
Yeah.
So this right here is going to be, this is going to look like on the bottom, 1 minus 1 plus.
So it is
So,
negative.
So it is a negative then, isn't it? We're subtracting 1 point something from 1, and so we're going to get an answer like positive over a small negative result on the bottom, right?
That makes sense.
So what's our answer?
Negative infinity.
Okay, I think an easier way to do it, you can look at the graph, but to me, I'm going back to the unit circle every time. If we look at the unit circle, much better circle. Still not
Look at
great.
this.
Better. So here's our pi fourths, right?
Yes.
There's pi fourths. So the ant is walking from this direction towards,
See,
Pi
to me,
fourths.
that seems like it's coming
Right.
from the left.
okay, and so what's going to be happening there? The ratio of tangent is going to be the y value divided by the x value, right? Everybody agree? So here's the place where they're equal. But for places up here, let's take just a sample point. Like if I take a point right up there, someplace that's a value of theta bigger than pi fourths, right? What's the ratio going to be? That coordinate, the y coordinate, is greater than 1, and the x coordinate is less than 1. Everybody see that?
Yeah.
Okay, I get big Y, small x, and so that's telling me that I'm getting a value greater than 1. That make sense?
Yeah.
Okay, so that's giving us that picture right there gives us our 1 plus on the bottom. Okay, because this is, and when we talk about, we talk about angles here, right? This is the theta we're talking about. So it's a little bit counterintuitive. If we're approaching from the positive direction, that means we're approaching from bigger angles, walking back towards smaller angles. Right?
Yeah.
Okay. Just wanted to get you thinking about that. Okay. All right. Work.
Do we have a new assignment?
You have just you have a new one. I don't think